let's spice in things up just a little bit here. I want to take a look at the other chain rule with two independent variables. Before, in the last example, we did something like this. X would be like 1 over t, and y be like t over 7 or something like that. But now what's going on is x is a function of two variables. So z is a function of x and y, but both x and y are functions of two other variables, s and t. Now here, s and t are in fact the independent variables. These are the independent variables. And x and y, these guys are actually referred to as the intermediate variables. And then z is, of course, the dependent variable. So let's take a look at how we do this. Given z equals f of xy, where x is a function of s and t, and y equals h of st, again another function of s and t, the partial of z with respect to s, see this could be treating t in this case as if t was a constant, this could be equal to the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. That's probably exactly what you were just thinking. So in this case, with z being equal to e to the x plus 2y, that would then give us the partial of z with respect to x. I need to take the derivative of this with respect to x, which is going to be e to the x plus 2y times the derivative of this with respect to x, which is just 1, so I don't need to really write it, but I guess I could for completeness, times the partial of x with respect to s. Well, with respect to s, t is just a constant, so this is like s over 7 or something like that, so the derivative would just be 1 over t. Again, keep in mind, with respect to s, t is a constant. Plus the partial of z with respect to y, again that's going to be e raised to the x plus 2y, times the derivative of this with respect to y, which is going to be 2, times the derivative of y with respect to s. So this is going to be equal to a negative t over s squared. So if I factor out the e x to the 2y, I'll get this being equal to e to the x plus 2y times, let's see what's left here. I'm going to have a 1 over t minus 2t over s squared. So here's my partial with respect to s, but actually I need to finish this up because I need to substitute back in the values for x and y here, which is going to be e to the, x was s over t, so this would be s over t plus 2 times y, which is t over s, times 1 over t plus 2t over s squared. So this would be my partial with respect to s. Now notice I still have t's in here because t is a constant in this case. So to do the same thing now, to take the partial of z with respect to t, I will have the partial of z with respect to x times the partial of x with respect to t plus the partial of z with respect to y times the partial of y with respect to t. It's the exact same idea, only I'm using t. So that's going to give me e to the x plus 2y times 1 times the derivative of x with respect to t. Well, x with respect to t will be a negative s over t squared plus the partial of z with respect to y. Again, I'm going to end up with e to the x plus 2y times 2 times the derivative of y, the partial of y with respect to t, which is going to be simply 1 over s. So again, I think I'm going to factor out this e. So I will end up having e to the x plus 2y times, that's a negative, so I'm going to put it second. I'm going to turn things around a little bit. This is simply 2 over s minus s over t squared. So that's what we ended up with for this particular example. But of course, we need to substitute in these values for x and y. Now, yeah, let's go ahead and do that. So this is going to be equal to e. See, x was s over t, so let's raise to the s over t, plus 2 times y, which is t over s, so I'm going to write it as 2t over s, times 2 over s minus s over t squared. Now notice here that f of xy is actually discontinuous for s being equal to t being equal to 0. Because when t and s are both 0, I've got a 0 over 0 situation here. And likewise, if I take a look at the partials, these partials end up with s and t in the denominator. So here, well, let's go to this one. For here, if s and t were 0, I'd have 0 over 0, 0 over 0, 2 over 0 minus 0 over 0. I mean, the thing's just a mess. So there's no doubt that s equals t equals 0 is definitely an issue. Now, one last thing I want to do is go ahead and do a substitution first. So I have f of x, y being equal to e to the x plus 2y. And again, just as a reminder, x equals s over t, and y was equal to t over s. So if I substitute this into my e to the x plus 2y, I'll end up with f of s and t, which would be e to the s over t plus 2t over s. Now, if I take my partials, the partial of z, whoops, that's a z, with respect to t will be e to the s over t plus 2t over s times the derivative of all this with respect to t, which is a negative s over t squared plus 2 over s. And the partial, and obviously I would probably turn those around, but that's okay for right now. The partial of z with respect to s is going to be e to the s over t plus 2t over s times the derivative of this with respect to s, which would be 1 over t. This will give me a minus 2t over s squared, which is exactly what we ended up with up here. That is that one, and this one is right here. Well, actually, it's right here once I substitute it all in. So again, in this particular instance, it was actually easier to substitute in those functions that represented x and y, and then take the partials directly rather than using the chain rule. We did use a chain rule, but we used a chain rule that's more akin to exactly what we did back in Calc 1. Don't ever forget how to apply this chain rule, because like I said before, there are times when you're really going to need it. Doing a substitution and trying to do like these two examples that just came out would be a really tough thing to do.